Perfect. So welcome everyone. So today I'm going to talk about the formulation for probabilistic softmax and remax function. So the outline of the talk today, first before going to the outline, what is softmax? Okay, some of you might have heard about it, many of you might not. So let's assume that we start with a real valued vector in n dimensions. Okay? And what we want is to pass this vector in a softmax function, so such that if we pass the vector and the component I, so an indicator variable, we want an output A. And that output A is going to be computed by the exponential of the ith component of my z vector divided by the sum of the exponential of all the components of my vector. Okay? And this output is going to be somewhere between 0 and 1. And the property of that softmax function is that if we make the sum over all possible components of A, is going to sum to 1, such that AI can be interpreted as a probability associated with the ith component of this. Okay, so we want to go from an n-dimensional real value vector to a probability in n dimension. Okay, so this is what softmax is intended for. So what we're going to see today is what is the reason of being of softmax in TAGI, why are we not using it? Then we're going to look at attention mechanism that also needs softmax, and this is going to be the principal reason why we're developing this. And then the core of the presentation is going to be about how can we obtain a closed form softmax and a better version that I call a remax function. We're going to see how and we're going to see why. So first, let's go back at the kind of usual slide, introduction of the notation for feed-forward neural network. Here it's a regression setup. Okay, we have our input layer X, we have some activation units in 2 layers here. So again, activation units are nonlinear transformation of hidden units, Z, and we go from different hidden layers by simply going from the layer of activation units at hidden layer 1, multiply by a vector of weights, add them all up, and add a component B1. So that's going to give me my Z, which is, where's my pointer? Z, which is going to be my hidden units at second layer for my first component. Perfect. Then we have, in the case of regression, as many output node on our output layer as I have kind of quantity I want to predict with my neural network. So in this case, I have Y output that I want to predict. I'm going to have Y node on my output layers, and Y's here are the actual observations. So ZO is the output of the neural net, Y is the actual observation. Okay? So this is for a regression setup. What happened now in a classification setup? Okay, in a classification setup, this part here is the same thing. Right now I just presented it as a simple multilinear perceptron and simple MLP, but if it would be a full CNN, it would be the same. Okay, as an input you would have, for instance, all the pixels in an image, you would have an additional filter, but the thing remains the same. What we're interested in here is the output layer, which is always the same no matter what is the architecture. What you're going to have, instead of having as many classes as what you want to predict, or as many variables as what you want to predict, you're going to have as many variables on the output layer as you have classes. And this, you're going to have 10 classes, you're going to have 10 variables here that are all in the real space, minus infinity to plus infinity. In C's are your classes. So this is real values, this is classes. So classes are going to be 0 or 1 in C dimensions. Okay? So here, what we would use in between is the softmax. So this is the classical way that deep learning works. So we're going to make softmax of the real value vector Z output, and we're going to look for the ith component is going to return the probability of class I. Okay, this is what is business as usual for classification in neural nets. And again, this is exactly the same calculation, exponential of Zi over the sum of exponential for all the components of the vector. The issue why we don't use this with TAGI is that there's no closed form solution if we say that Z output, my vector here, is uncertain. So we have a Gaussian vector with mean mu and diagonal covariance matrix, so identity times sigma. We don't have a closed form solution to this. Okay? So we didn't use this in TAGI. What we actually use in TAGI is what is called hierarchical softmax. Okay, and here I illustrated for an example where we have 4 classes. Okay, so now you see we don't have as many hidden state on the output layer as I have class. It's n minus 1. Why? Because I don't have the softmax anymore. What I have are gates. In that case, for 4 classes, I need 3 gates. And these gates decides, for instance, the first gate, am I going to go for class 1 or 2? Or am I going to go for class 3 or 4? Then the gate 2-1 decides between class 1 and class 2. The gates 2-2 between class 3 and class 4. Okay, and depending what side of the gate we're going to choose, depend on the value on the output layer of the neural net. So my first hidden state here, decide am I going to go up or down for that first gate. And how am I going to do this? Through a normal CDF. Why? Because it turned out that if Z output is Gaussian, we have a closed form solution to marginalize the uncertainty about Z through that Gaussian CDF, centered at 0. So the closed form solution to that integration is the normal CDF evaluated for mu divided by square root of 3 plus sigma squared. 3 is a hyperparameter, we're going to assume it's fixed for now. Okay, but the key part here is that if Z is uncertain here, we have that closed form solution to probabilistically handle this. Okay, what happened here? If sigma is very large, for a given mu, if sigma is very large, what's going to happen? Denominator gets very large. So whatever on something very large gets 0. 0, you're going to have a probability of 0.5. Okay, so as soon as your uncertainty grows large, you say I can either go left or right. Okay, so that automatically accounts for the amount of uncertainty you have about your hidden state. And this is all closed form, this is all exact. So this is just for going left or right, or up or down. But if I have probability of phi of Z1, I know that the probability of going the other branch is 1 minus n. So it's very easy. It's the complement of the probability. And again, 1 minus the CDF can be directly evaluated as phi of minus Z1, because this is symmetric around 0. Okay, so it's always the same thing to go up or down. Then we have our first hidden state, control this gate. So same thing going up, going down. And now, can you guys tell me what is the probability of C1?
Probability of
phi of Z1 times phi of Z21. The product of the two will make me the probability of C1. So in that case, probability of C1 is this one times this one, probability of Z2, this one times this one. Okay, this is how it works. Then we can do the same thing with my third hidden state, control my third gate, and we can get the probability of any of the possibilities. Okay, so far so good? So this is a simple case, we have 4 classes. So where does that hierarchical softmax shines? So if we have only 2 classes, I need 1 gate. A gate here is represented by this kind of little dot. And I have just 1 level of gating. What if I have 4 classes? I need, as in the previous example, 3 gates on 2 levels. What if I have 8 gates? 8 classes. How many gates?
7.
7 gates on how many layers? 3 layers. Okay?
Wow.
So it's always multiplied by 2. 16, 4 level, I'm going to have 16 minus 1, 15 gates. Okay? 32. So you see the picture here. Okay? So let's imagine we have 32 classes, like here. So the probability of any classes here can be computed by simply taking the product of 5 normal CDF. Okay, what if instead of having only 32 classes, I have a big problem, I have 1,000,000 classes. Then I will only need 20 levels to model 1,000,000 classes. What if I have 10 to the 80 classes? That's a big number. Okay, then I can model the probability of any class by only taking the product of 266 number. And why I say 10 to the 80 is a large number, this is actually a proportion of the order of magnitude of the number of atoms in the universe. Okay, so once you're there, you're pretty large. And we can model this with a fairly limited number of hidden states. This is where this hierarchical softmax shine, because we can represent a very large number of classes with a small number of hidden variables. So this is what actually we're using in TAGI, both because it's very efficient and because we have closed form solution for marginalizing uncertainty through it. So from the start, this is what we've been using. However, the problem is this the hierarchical softmax is not compatible with attention mechanism. So if we want to start using it, we can't use that. It's not compatible. We're going to see why. So again, a little recap of how attention mechanism work. In this case, it's about translation. So imagine we have some Russian here, so we can either ask Ali or we can ask Google Translate to do it, but how it works behind if we want to work with an attention mechanism. I want to translate this, which means I saw a cat on map, to, in English, I saw a cat on the map. Okay? This is a very crude way of picturing it. I just wanted to give you the idea. But basically how it would work, we would encode each of those words into a latent space. This is what these points represent. So each word has its own encoding in the latent space. Then when we try to decode, to predict what is the translated version, we have the encoded version of all our traduced version. Okay, or translated version, sorry. And so the last word we're currently at is I saw a. Okay, and now we need to predict the next word. But then we need to put, if we want to use attention mechanism, we want to say on which of the word from the original sentence we need to put weight. If I saw a, do I need to put weight on one? Probably not. On map, probably not meter, okay? But cat is probably a word I really want to use to predict my next word. Okay? So I don't know how to present Scoto or something like this.
Katu.
Come on, oh?
Katu.
Katu. So you see? So how do we do this? We need to assign weights to any of those, so attention weights. And how do we define the attention weights? We're going to pass the latent encoding of each word, and we're going to compare it with the latent encoding of where we're currently at for predicting the next one. So we're going to pass as input to a, say, multi-layer perceptron, these two vectors of encoded state for both or sentence or word in the original sentence versus the current state we are at, because we want to predict the next word. So this is the input vector to our neural net. And the output is going to be a real value score, okay, between minus infinity and plus infinity. And we're going to have compared this current latent representation to all the possible words we have in what we want to translate, to find where do we want to push attention. So then what we're going to have is as many scores as we have words in our sentence we want to translate. And we're going to pass these scores, which are all real numbers, into the softmax to assign probabilities to each of those words. Okay, here you have to see that it's not directly a classification problem as we had before. Okay, it's a sequence of different comparisons that gives a score. And that number of comparisons might differ from one sentence to the other. So it's not fixed like before in terms of number of classes. That's why we can't use the hierarchical softmax, and we have to use the classical softmax. Okay, here we're going to say, okay, but we don't do any translation in this group. Yeah, of course we don't do translation. We don't want to use this for translation. We want to use it for time series prediction. Okay, and we want to start using attention mechanism to explore its potential for time series forecasting. So in this case, this is an example for dual stage attention-based RNNs, where on the left part, we have an attention that is applied to the explanatory time series. So in the case of dams, it would be water level, it would be temperature, it would be humidity, it would be precipitation, etc. These explanatory time series that explain the behavior of the dam. So we want to say at each time, how much attention should we put on any of those time series? Okay, so we're going to do the same. We're going to compare the hidden state vector from, say, at LSTM, at current time or at the previous time t-1, with the latent representation of each of those time series. Then we're going to compute the attention weights that are going to weight in the input vector from each of those time series. Okay, this is the first stage, that dual stage. The second stage is going to be about applying weights to each piece of information from the current time step to the first time step in the time series from the past. Okay, so we have a dual stage where we're going to get out the comparison of latent representation, and at the end is going to provide attention weights to say to what time step in the past should we kind of pay attention to. And again, both cases require softmax. Okay, so that's why we need that softmax function. So this is why we're talking about softmax today. So the softmax function, as we said, so what we're going to do now is to say how can we have a closed form softmax when we have probabilistic or Gaussian inputs to that function. So let's just assume we have a vector of hidden state z1 to zc, c being a number of classes, where the probability of each output is going to be A, the output of my softmax, which is defined following this function. So AI is going to be, as I said earlier, exponential of zi divided by the sum over all possible classes, the exponential of each component of my vector. Okay? So in terms of to shorten the notation, I'm just going to say sum over the exponential of a vector. Okay, but I mean exactly the same thing as what I have here. Then the question we want to answer today is how can we make a probabilistic version of softmax when z is not deterministic, but where z is a Gaussian vector with mean mu z and diagonal covariance matrix. So I have an identity matrix times a variance vector. Okay? Can we use GMA to do this? Gaussian multivariate approximation. Ali?
I think so, I don't know.
Because with GMA, we can make the product of random variable, right? But here we need to have a division. And GMA can do division. We can only do product. Okay? Now what we need here is to divide two quantities. And GMA cannot be applied there. We tried it, doesn't work. Okay? So what we're going to try instead is to leverage the property of log normal random variables. Okay, let's recap what are the key properties of these log normal. So we can say that the random variable z is going to be log normal if the log of z is normal. Okay, I can understand it's confusing, but we're going to break that down in smaller pieces. We can also say, the other side of the coin, that the exponential of z is log normal if z is normal. So we have a variable z that is normal. We're going to take the exponential of that variable. It's going to become log normal. Okay? We're going to explore this. So this second option. We have our variable z. This is its PDF. Okay? Mean 2, standard deviation 1. So this is normal, or this is Gaussian. Mean mu z, variance sigma z squared. Then we say we take the exponential of it. And this should be normal. Indeed, it is should be log normal. And indeed, this is log normal. This is a PDF of just taking the exponential of z, which is normal. Okay? And so exponential of z is distributed like a log normal, where the parameter of this log normal are actually the mean and standard deviation from z. Okay, so this is how, without any calculation, we can define that log normal PDF. Okay? Now, I can compute the expected value of z, because this is not the expected value of z. This is the expected value of z, but I want to compute the expected value of exponential of z. And I can do this using this closed form function. I can calculate the variance for exponential of z using this closed form function. Okay? To simplify the notation, instead of using capital E and V, I'm going to use mu of exponential of z and sigma square of exponential of z. Okay? And now what I can do as well is I can say that theoretically I know that I'm 100% right, theoretically right, by saying that exponential of z is log normal. However, here I'm going to make a rather crude approximation by saying, what if I use the moments mu of exponential of z and variance of exponential of z to model this as a normal random variable? Okay, that's going to look like this yellow curve. Is it a good approximation? Not so much. Okay? Why? Because I have still a big part of the domain that is in the negative. What if I shrink the variance? Okay, if I make it half as small, it's a little better. Half as small again, it's much better. Okay, if you have a large part of your normal variable that goes in the negative domain, it's not going to be a good approximation. But if you go away from zero, it becomes a fairly close approximation. So just taking the moments here for the mean and variance of exponential of z, and assigning it to a normal variable, or taking the log normal, it's pretty much the same. Or not the same, but it's close. Okay, it's a reasonable approximation. Then, if we want to look, because we're going to need that to learn, we might need the covariance between exponential of z and z. We add it with a closed form solution here. And this is it for the first part. Then we're going to look at the reverse story. Okay, so now we said that z is normal, and say exponential of z is going to be log. Then we're going to look at the first statement here, saying that if ln of z is normal, then z should be log normal. Okay, so now we have ln of z, which is normal. So this here we're going to assume here ln of z, which is normal here. Again, the same thing. So z should be log normal. Okay? So the same thing. So z here should be log normal. These were kind of flipped compared to before. Now I can approximate z again by the same normal, for which I already have mu z and sigma z. Where the sigma from mu z and sigma z, how do I compute the variance of ln of z and the mean of ln of z from these, again, closed form solution. Okay, this you can find in any textbook. And again, we have a closed form solution for the covariance between z and the log of z. Perfect. So now what are the key properties we're going to use for softmax? So the sum of log normal random variable, it's nothing. Okay, there's no closed form distribution associated with it. Okay, it's just sum. There's no, it's not log normal, it's not normal, it's not anything else. Okay, perfect. So we can leverage this. What about the product of the log normal? Perfect, we know it's log normal. But if we don't have a product, we have a division. But turns out the division is the same. Division of log normal random variables are also log normal. Okay? So with softmax, we're going to have two terms that are divided. So we're going to be able to leverage this in order to perform our division probabilistically. Okay? So let's look how can we build that closed form probabilistic softmax. So the equation again, I remind you, exponential of zi, the ith component of my vector, divided by the sum of the exponential of any component in my vector. This is my kind of normalization constant. So here I have an example where I have 5 variables. Okay, z's are the real value quantities that are described by normal. Okay, so you see that my z0 is very close to 1. All the other ones are very close to -1. So when we're going to compute probability, I should assume a high probability for this one, low probability for the 4 other classes. Here, this is mean plus or minus 1 standard deviation. This is what the viscous represents. Then this is the PDF for z0, the first one. This is as given mean and standard deviation. Perfect. So my vector is mu z. I have an identity matrix, so diagonal covariance matrix, and a variance vector. Okay. Then any component is also normal. Perfect. Then what is going to be exponential of z? Because this is what I need on the denominator. What's going to be the distribution from what we saw earlier?
Log normal.
It's going to be log normal. You take it normal, you take the exponential, it's going to be log normal. Perfect, and we have already all the equations to calculate this. So what I'm going to have here is going to be the exponential, what I have on my numerator here. I know the closed form PDF for this is going to be log normal with parameters mu z and sigma z. Perfect. The sum of normal, we said it's normal. Okay? But what we need on the denominator is not going to be the sum of normal. It's going to be the sum of log normal. We can't do that. Okay? So what we're going to need to do is to transform our variables so that we can approximate these log normals by a normal, so that we can have the sum of them being a normal. So we're going to take the equivalent, we're going to call this exponential of z e for short n, and we're going to compute the expected value of e and the variance of e. Okay, our exponential variable here. To model that true PDF that would be in dash log normal by instead of normal. Okay? And what are the mu e and sigma e? I put them in gray because I don't care about what is the specific terms in there. I just want you to know that they are closed form solution, textbook solution to find these moments. Okay, perfect. So now I have here in black a normal approximation, and you see it's pretty close to my log normal. That now I can sum to obtain my denominator term here, because the sum of normal is going to be normal. So here I can have my denominator, the sum of all my exponentials of my vector, that I know it's going to be normal. So that sum, I'm going to call it E tilde, is going to be normal with mean mu e, variance sigma e squared. So mu e tilde is going to be the sum of the mean of each component. The variance is going to be the sum of each of the variants, because all the terms are supposed to be independent from each other from this hypothesis here. Okay? Then the covariance between ei and E tilde, we're going to need that later on. What is it? Anyone knows? It's written there, but why is it this? So E tilde is the sum of all e's. Why can I say that the covariance between E and E tilde is simply the variance of EI? The ith component of my vector.
Independence plays a role here.
Because in the independence, if we would make, imagine that we make a matrix that only would be a vector of ones. if it would be A times a diagonal matrix times A transpose, we would see that we would only get this term squared. Okay? Sorry, A times this term, because the covariance is only A times this diagonal. Okay, we would only get sigma E squared. This is the only variable that contributes to the sum. So it's only the sum of the variable only depends on the variance of each variable individually. Okay? So again, all of this is textbooks material in terms of all of these relations are available. I didn't develop anything yet. Okay, so now we have the sum that is going to be normal. We have the numerator that is log normal. But the division of log normal divided by normal is not defined. I need my denominator to be log normal for being able to apply that application. So what I then need to do is to transform that sum, that normal PDF, into a log normal PDF, which is now represented by that blue dashed line. The approximation is still pretty good. Okay, we can compare this and this. These are the two PDF. This is the numerator here. This is the denominator there, which are both log normal. I can divide analytically. Okay? So this is what I'm going to do. I have my two log normal PDF. The parameter for this guy I can compute again analytically. Don't care about the relationship, but these are textbooks relationship. And now I can perform my division. Okay? So my division, what I want to compute is A. A is going to be the output of my softmax, which is going to be now log normal because it's the division of two log normal distribution. I need to compute mu of ln of A, sigma of ln of A, and I can obtain it from these relationship, where this relationship is going to be simply the difference between the parameter in the log space, so mu z minus mu ln of E, the summation of the variance, so sigma z squared plus sigma ln of E squared, minus 2 times the covariance. This is the standard relationship for the addition or subtraction of, in this case, subtraction of Gaussian random variables, because we're working in the log transform space. So the only thing I need to define is that covariance, and that covariance, again, textbooks material, I get this relationship, which intervene the covariance between EI and E tilde, where we say we already have previously. So we have everything here to find everything in this case. Why we need that covariance? Because you see that both in the numerator and denominator, the same quantity appears. So here we have Zi, and in the sum of Zi, we have Zi as well. So we need to take into account that dependency, where Zi appear both on the numerator and the denominator. So this is what these terms account for. So perfect, but now the last step I need is that A is log normal. If I want to use this in TAGI, I need to transform it as a normal. Okay, so again, I'm going to apply the approximation, and you see those two approximations are so good that they're on top of each other. Normal and log normal are straight on top of each other. And the moments can be computed analytically using these relationships. Okay? So perfect, and now once I have all these distributions, I can plot the mean plus and minus 1 standard deviation for each of them. That would be my output from the softmax. We said that here we expect a high probability. It's probability of about 80% for this one, and the variable probability for all of the other ones. Okay? And we can compare with the dots you can see there, is that if we would just use, instead of using the random variable itself, just mu z into softmax, kind of the deterministic version. It would give the value given by the points there, showing that it's really actually computing the real quantity, except in this case a deterministic version. Okay? So now we're going to look at the issues with softmax. So I prepare a couple of examples. The real life demos, this is always dangerous.
And it's in Python.
And it's in Python. So for me, double danger. Okay, so this is an example. We have now 10 variables. Okay, top here is are my z's. Okay, the real values quantity for 10 classes. So we see again, I always model my class 0 as having the higher probability. Okay, this is just a default choice I make. And all the other ones you see, so this one is around +1. All the other ones are around -1, but not exactly. Okay? Then I'm going to have m. M is representing the exponential of all these quantities. We see that how plot expected value plus -1 standard deviation looks like. So most of the uncertainty get killed because these are small values. Here I only represent z0, my first one. In dash blue is going to be the log normal. In black is going to be the normal approximation.
It's okay, it's not on top of it, but it's not a crazy approximation either. This is the log normal and the normal approximation for the sum of all my exponential of z. And on the bottom, what you see is the normal and log normal for the a here. So you see that in blue, this represents the expected value plus and minus 1 standard deviation. And what I have in green are the Monte Carlo calculation. So the green can be represented as ground truth. I generated 10,000 Monte Carlo samples to see what should be the real bounds I would obtain. So we see that here, I'm not too far from, you see that all these bounds collapse on themselves rightfully. This one, I overestimate a little bit the bounds of the uncertainty, but I'm still fairly good, okay? So this is a case where it works pretty well, okay? Let's see where it doesn't work. So this is my first case. So second case, we have the same thing, but now, what did I change? Let me check it, what did I change? Incorporating. So in the second case, okay, first case I have a small uncertainty on my variable, now I have a much larger uncertainty. Okay, assuming that my uncertainty is much larger, you see that my uncertainty gets much larger on my output, my approximations are fairly poor, and now you can see that my deterministic softmax tell me the probability should be 1, whereas my uncertainty for Monte Carlo or for what I estimate make a much broader range of possible values. Okay, so in this case it works, but the approximation, especially for the first variable, is off compared with Monte Carlo. Okay, the uncertainty is much too large due to the relatively poor approximation. Okay, this is for the second case. Now, what's going to happen in a third case, where instead of having 10 hidden units z, I'm going to have 50. Okay, I increase the number of hidden units. So if you remember before, my positive examples were z equal roughly plus 1, and the one that I have a low probability for class in the z space were minus 1. Okay, and now I could reach probability that we're close to 1 for my first class. Now we're going to see what happens if I increase the number of classes and keep those same relative values. So in that case, we're going to see that it will start to fail. Okay, so now what we see, if we keep the z0 around 1 and the z, all the other ones around, say, minus 1, we see that the probability drop drastically. Why? Because exponential of z always make a positive quantity. So my denominator, it keeps growing as I add classes, because I keep adding exponential of something that is non-zero. So since my denominator, the value keeps growing, the relative probability of my first class that hasn't moved decreases as I'm going to increase more and more variables. And this is a big problem for TAGI, because it's kind of a moving target. TAGI, we need to work always in standardized space between minus 1 and 1. And there, the problem is that we're going to need to increase drastically zi to 3, 4, 5 in order to have very high probability. And the more classes we're going to add, the more we're going to have to prop up the value of zi to compensate for the ever-growing denominator in softmax. And also another case that we can see here, the point is if we evaluate softmax deterministically just with the mean value, probability of the first class is 1. Okay, but we can see that from the ground truth in green, it's very far from 1. So we can see that the deterministic softmax won't cut the job for probabilistic setup. Our case is not too bad, because you see for all the variables, the green and blue bands, the blue band found to overestimate, but not by that much. We're still with a fairly good approximation, given that Monte Carlo is order of magnitude more expensive than our analytical expression, and it's fairly cheap. Okay? So in this case, we have the problem of the decrease in probability that will need to be compensated by a larger value of zi. Okay, so then we're going to see what's going to happen if we decrease the uncertainty. So uncertainty was 1, now uncertainty is going to be 0.25. When I say uncertainty, it's standard deviation. we should increase the probability. That works fairly well. So if we decrease the uncertainty about each of the variables, we get back a fairly high value. But what happens if on the opposite, we increase the probability? And you see for all the cases so far, we can see there's a little leakage of probability because the sum of all the expected value for the A's are slightly above 1. Okay? It should sum theoretically to 1. We have approximation, it doesn't sum exactly to 1, but it's not catastrophic. What happens now if we increase the amount of uncertainty? Okay, let's put it to 2 instead of putting it to 1. This is where it's going to break down. It's slow on ears because it's the Monte Carlo sample that run in the background. The approximation itself is fairly quick. So I haven't started. So you can see, now if I increase the uncertainty, you see that the quality of my approximation is not so good. My probability has dropped down to something very small. And it's funny because usually I get some very bad normalization constant. Oh! I'm not using the good one. Yeah, it was working because the other one, the new one is remax. So I showed you remax instead of showing you softmax. But basically, the previous case we're working pretty well, but where it breaks is this one. So you see the remax is what we're going to see next, what solved the problem. And if we run with softmax, this is what happened if we increase the uncertainty. Okay, everything explodes. Okay, the uncertainty are completely off. The Monte Carlo versus what we estimate is completely wrong. And the normalization constant goes to a wire. Okay, so it doesn't work well. As soon as we have high uncertainty, it won't cut it. So if we look at the other cases, so always when you do live demos, you forget something.
I saw the title, it said remax, so I was like, maybe it was just a typo.
So you see, I'm just going to show them quickly, but you'll see that there's not much difference. So the first cases works pretty well. So it's going to sum at 1, the first case. So you see 1.035, perfect. We have still fairly good agreement between the predicted with Monte Carlo and the estimated. Business as usual. If we look at the second one, this. So second one, again, I'm gonna, what am I gonna do? So second one, I simply increase the distance. So instead of being minus 1, 1, I increase with a distance of 2. So you say by increasing the distance of 2, I can maintain, or I can go closer to 1, perfect. If I increase the number of hidden states, where we say that it's gonna increase the probability, so you say as soon as I increase the number of variable, again, like before, the probability is going to drop down. I didn't change any of the value of z, I just increased the number. Then the probability automatically dropped. But then, as I said earlier, the fourth case is where it's problematic, is whenever I'm going to try to increase the uncertainty, this is when it's going to break. And this is problematic. Why? Because if we need to reach high values of z to have highly concentrated probability, I'll need very broad prior. And if I cannot have broad prior because everything explodes, I won't reach. So if I need to reach +5, and I'm stuck to a standard deviation of 1, I'll never reach 5. Because I'm going to constrain my prior. And exponential won't allow me to expand my prior. So it works well in a kind of deterministic context. It's not going to work well in the probabilistic set. Okay, so even if it kind of works, for practical purposes, it doesn't work well. Okay, so this is the issues with the softmax. Sorry for the spoiler for the remax, but we're going to come to it. So if we want to have AIs that are close to 1, so high probability for AI at pass, we're going to have as the number of A, the number of the classes, so it should have been C, as the number of classes increase, then the values of ZI needs to increase as well. So whenever we have 50, 100 classes, zi needs to be at like +5 and -5. Whereas when we have 5, we might have a BB at +1, -1 is sufficient. And the more classes we're going to add, the more we're going to need to expand the gap. The problem with expanding the gap, we can't handle sigmas, so the prior uncertainty for those z is larger than 1. So it's not going to work well. Then, whenever sigma is greater than 1, the uncertainty about the exponential explodes. So now the summation over the mean is much larger than 1. Times 4 or 5, it just breaks down. So, and the issue here is the exponential. Exponential is strongly nonlinear. It goes from extremely small to extremely large. It's not a good idea. Okay, so this is the problem. This is what we want to remove. And how do I suggest to remove this? With what we recently developed with the Gaussian mixture ReLU, okay, for shorthand ReLU. This is a new activation function, or just a new probabilistic treatment of the existing ReLU function. So now instead of using exponential, we're going to use simple ReLU. So ReLU is simply max of 0 and z. Okay, but now in our context, the input for z is going to be a Gaussian random variable. And how does that ReLU works? We're going to compute what you cannot see because it's yellow. It's a wrong choice of color, but the yellow part below 0 is the negative part. We're going to compute the area under this domain. There's going to be the probability that it's on that 0 domain. This is going to be represented by the height of the curve here, which is, the axis is reversed here. The height of this stem represents the probability of being less or equal to 0. Then what we're going to do is that we're going to see for the remaining part that is in red here, that is the positive part, this is going to be that dashed truncated Gaussian. And then we're going to compute the moment of that truncated Gaussian and associate it with the Gaussian random variable. And then what we're going to do, the mixture between 0 times this probability plus the complement of this probability times that red curve. That's going to give me that mixture in blue here. Since you see that that probability is almost 1, it really shrinks the probability constant and the expected value, put it towards 0. This is in the first case where we have a sigma z which is constant and we have a small negative mean. What if we have a small positive mean? The constant of the positive value gets a little larger, the probability of negative value drops, and we see that we have a larger uncertainty. What if we have a large positive mean? We have 0 constant almost in the negative domain, so this drops to 0, and this is identical to this. Okay, if we look at a second case where we're going to modify sigma and keep mean constant. So we're going to keep mu z in the negative domain and constant, and we're going to look at a small, medium, and large case for the variance. If you have small variance, you see that all the probability constant is in negative value. You have virtually no uncertainty. We're at 0. If we shift it a little bit, or if we increase the variance a bit, we're going to increase the amount in the positive domain. We're going to have a little more uncertainty. If we increase very vastly the uncertainty, we're going to have a large part in, or a significant part in the positive domain. We're going to have substantial variance here. Okay, this is the essence of ReLU that I want to use to replace the exponential. If we look visually, how does it look like? It's somehow like this for different values of sigma of mu z, different values of standard deviation. This is the plain line is the output expected value. The shaded region, the plus and minus 1 sigma region. We have the same thing if we only look with respect to the z-axis, it would look like this for each of those curves. So theoretically, how does it work? We're going to look at the median variance for the truncated Gaussian, for the positive part. We need to compute alpha, the ratio between mu z and sigma z. Omega is going to be the probability that z is greater than 0. So 1 minus the normal CDF of the alpha we have here, minus mu z over sigma z. Beta is going to be a scaling factor for the mean of the truncated Gaussian. So it's going to be the original mean mu, plus beta, which is going to be greater than 0, times sigma. So we're always going to push the mean toward positive value. So the resulting truncated mean is always going to be larger than the original one. Then we're going to scale the truncated variance by a factor kappa, computed here. And finally, A is going to be the mixture. So it's going to be the complement of the probability being greater than 0, so probability of the negative values times 0, plus omega, that probability greater than 0, times our truncated Gaussian z tilde. So we can compute the mean as being complement of omega times 0 plus omega times mu z of our truncated Gaussian. Omega times 0 plus, no, complement of omega times 0 times omega plus the variance of z plus this term, which is the variance representing the distance between that 0 certainty and the mean of our truncated Gaussian. So I'm skipping some stuff, but this is the essence of how it would work. Now comes the probabilistic closed form, probabilistic remax. Okay, re for really. Okay, so in this case, we're going to replace the exponential by that m real function. We have the same starting point z, which is normal, mean vector mu z, and diagonal covariance matrix. Then zi, the ith component, is going to be normal. We're going to pass z through an m real function where we've seen previously how to compute those moments. So we start from normal, we end up at the output from the m real being normal as well. We can plot mean plus and minus 1 standard deviation for each again. The sum of normal is normal. So from what I have here, I can directly compute what I have on my denominator there. So it's going to be the sum of each respective mean, the sum of covariance, the sum of the respective variance, and the covariance is the same thing as we had before. Done deal. Now, the division of normal, we said it's not normal, we need to go in the log transform space. Okay, so I need to transform this quantity in the log transform space, this quantity as well. So the first one here is going to be a log normal. I need to compute these two quantities. I have closed form solution to do it. I need to do the same thing for the sum. I have closed form solution to do it. So now in the blue dash is my log normal approximation. In blue dash, my log normal approximation. These are log normal. I can now subtract them to make the division. So this is what I do here to obtain my A. I have closed form solution to do this. This term here, I can develop it where the same thing we had before appears. So now I can have that approximation for a log normal. I need a normal to use it in TGI. So I'm going to transform it in a normal space using these relations. Okay? And now we can plot the result of these mu A similar. Okay? And I'm just going to redo it quickly, but what we saw is that even if we have very large value for the remax, it's still going to give good results. So even if we have the same thing, so 50 hidden units with large variance, you see that all the variance, the green is the Monte Carlo, the blue is what we compute with the probabilistic remax, are really in close match. And here the dot would be just the deterministic value with the mean, it's completely off. Okay, we need to compute the uncertainty, and we see that our approximation is fairly good compared to the ground truth. So if you look at another example that would be more striking, so with small uncertainty instead of large uncertainty. And note that you see that we have a very good approximation and very close uncertainty bounds, and it always normalized, contrarily to the exponential that which will not. So this is it for the demos. So in conclusion, the probabilistic softmax is not suited for TGI. Okay, because as the number of classes are going to grow, I'm going to have a moving target. I'm going to be always chasing higher value of Z, which is not going to work well with the kind of the standardized nature of TGI. Then this is what I said, for as the number of classes increases, you're ever going to have larger and larger value for ZI, for the one to represent high probability. And again, whenever the uncertainty on Z is large, you want to chase large value, the exponential formulation is going to break down. So the probabilistic remax function solves those limitations. It can replace the hierarchical softmax in classification task. From the preliminary results that we got from A, it doesn't outperform what we currently have, but it can be a substitute. And what we want to use it for is now to build probabilistic attention mechanism, especially in our case for time series model. If ever we would want to model a full covariance version for this, instead of having a diagonal covariance and full covariance, I see no roadblock into it. We could do it as well. It's going to be more expensive, but it would be compatible with it as well. So overall, remax is better than softmax, but we still have some issues. We're still, if we look at the sum of the mean, still slightly above 1. Okay, sometimes we get 1.02, 1.03. I haven't fully investigated how could we remove this. And also the sigma A, so the viscous for our remax probabilistic formulation, are slightly larger than from the Monte Carlo estimate. Okay, we're always slightly overestimating compared to the truth. I haven't found any solution to this yet. So that's all.
questions, comments?
Sure. I have a question. If you could explain how you obtain the Monte Carlo estimates, and also like the mean that you said. Is that the target variable that you use?
So like, let's take this one for instance. So what I'm gonna do is let's go back. So I'm gonna be here, I have my vector z. I'm gonna draw 10,000 sample of this 5-dimensional vector. So I'm gonna have a matrix 10,000 by 5. I'm gonna pass each one of those lines into MReLU or remax or softmax, which is that each component I'm gonna take MReLU of it by the sample itself, divide by the sum of MReLU of all the samples. So for each vector of sample, I'm gonna have a vector of AI, which are the real ground truth realization. And then I'm gonna have, again, a matrix of 10,000 times 5. And what I can do is compute the mean and standard deviation for this population of sample. And through this, I can get the ground truth of what should be the true output moment.
But we're still assuming it's like normal.
Yeah, we want to say for that setup, what should be the theoretical answer. Okay.
If it is indeed normal.
If it is indeed normal. Okay, it's for all kind of a closed world where all the other assumptions would hold.
Okay. How
good is just this approximation? Then if z would be not normal, then it doesn't hold at all. Or it's going to depart from it. You had a second question, or?
No, and then, because you said also the mean value, you were showing some mean.
Yeah. So
which was deterministic, you said.
Exactly. So I do the same thing. Instead of using population of samples, I only use mu z. So MReLU of mu z divided by the sum of mu z.
Got it.
Okay, if we completely omit the uncertainty about z. And what we saw that in this case, which is for example, it worked, but from other case where we would have large uncertainty, so if we take the last case for example, you see the expected value is 1, but you see the probabilistic metrics are very far from 1. So using just the mean value would be completely up.
Thank you.
Other questions, comments?
I'm thinking what would be the issue with the sum of mean value slightly bigger than 1, like in reality.
In reality, what would be the issue with this? The probability of the sum of all your class is not going to be 1. It's kind of suboptimal because the probability by definition must sum to 1. Here, the disagreement between our approximate and reality is small, so the impact is going to be small, but still, it's a sign that there's an approximation. In the case of the attention mechanism, I assume it's not going to be as important as it was for the, as it would be for classification.
Is it coming from the fact that you're going from normal to log normal, dividing and then coming back?
I mean, this is the only thing I'm doing, so it must come from there. but I don't know exactly where and in what circumstances is the boundary. Okay, I've spent like not much time on this, so I haven't finished exploring all the ins and outs and the implication, the possible solution to it. But you're right, in approximate somewhere in all those transformation, it entails some approximation, but I don't know exactly which one is contribute the most to the approximation. Is it the sum of the denominator? Is it division? What is it? Not sure.
I'm thinking like, because whenever we are too close to the bound, would it be possible that
which bound?
The zero bound, the ReLU.
Okay. So that all having small values.
Yeah. Would it be possible that when we go log normal and back to normal, that my mean would be shifted into negative to mean?
No. No, because actually I didn't put it here because it's a kind of hat trick. I found it too complex. But I actually, when I did test, initially it happened. Because if, for instance, I give z's, which are all going to be mean minus 10, and standard deviation 1.
So all my n ReLU by numerical error would get in the negative domain. It can happen. It can happen when you're very far out in the negative domain, that when you make that correction, mu z plus beta sigma z, that beta here is gonna bring it in the negative domain. Okay, but this is numerical error. It's gonna bring it by 10 to the minus 15, but this is enough to break it.
Yeah.
So here, I didn't put it, but in the code it's there. I have max of 10 to the minus 6 and this. Just to be sure that if ever we have these numerical errors, it doesn't completely mess up the whole thing. So I have it somewhere here, that criteria.
It's up there, it says omega, right there, and Pmax. Yeah.
Yeah, but this is another one. Yeah, it must be a this one. So you see, the maximum of the mean that is computed are 10 to the minus 6. The first one is already there. Okay, this first one is there, it's this one. Because here, if omega, the probability, gets too small, it's going to get 0 and you're going to have a division by 0. Okay, so it's just to prevent a division by 0. This is the first one you can see here, so I even lower it to 10 to the minus 6. The second one is just to say that if the value goes negative, use 10 to the e to the minus 6. Okay, but it's a good comment.
Does it matter which kind of data type you're working with?
What do you mean by data
like
type?
for example, like so you
Like
compute
int8 or
exactly, yeah, like that.
I've not explored. Right now it's just regular floats, but like int8 wouldn't work. But
yeah.
if we use like lower like half precision, I don't think it would matter.
No, I was saying like maybe is it if you increase the precision, the number will go down like that error.
Oh, it could, but this is expensive. So right now, like for instance, in TAGI, we're working in single precision, and it's just a matter of not being able to do the calculation right away, but eventually we want to go into half precision because it's much faster to do the calculation. So the overall framework pushed us to go lower precision, not more, because we don't need that extra precision. But that could, if we want to solve these issues, higher precision might solve it. But in our case, these little errors made no big consequences in our end results. It's negligible changes, besides when we get caught in a numerical crash.
This is the hierarchical is better than this?
Classification, yes. Seriously, for me, if I would have to recommend something for classification, I still push for hierarchical. The theory is really clean, it scales, it works well, we have very good performance. However, we can't use, and I really scratched my head into thinking, how can we use that hierarchical intervention? It doesn't work because it really requires a fixed number of classes. And these classes, you can't permute them. Class 3 cannot become class 1 because it has a fixed gating mechanism. Whereas with softmax, you can permute 2 classes, it doesn't change. You can do this with that hierarchical. And since that attention mechanism requires a comparison of sequences of different comparison, and then you want to weight them up to probability, intrinsically, it doesn't necessarily need to be softmax, but it cannot be hierarchical softmax.
James, can you go to the equation for the remax? Yeah, this one on the right, top right. So I just wondering. So you have tried to push so you have z value, right? And then you go use a exponential function for z.
This is what we use in the normal softmax.
Yes, and then you use m ReLU for z, right?
Yeah.
So and then you because the division cannot be done with by normal.
Yeah.
So that you
always transform by log normal.
Yeah, approximate them by log normal. So my question is, why don't you just instead of using m ReLU, you just do with the raw with the value of z, the original value of z.
So z divided by sum of z.
Yeah, and then use the log normal.
Because if I just do z divided by sum of z, I can have positive and negative value. So I'm not going to get probabilities. because the output can be either positive or negative. It needs to be restricted to be positive here, so that the end probabilities must be between 0 and 1. If I use z and zi is negative, I'm going to have negative probability. We could use absolute of z divided by sum of absolute values. Or we can use square of z divided by sum of squares. So n really is not the only choice, but just z wouldn't work.
Okay, just okay.
I have a question. Is the transformation to log normal is performed on the sum, on the results of the sum, or is it performed one by one?
Both. So the transformation log normal, because on the numerator, we're going to need them one by one, and then we compute the sum, and we transform the sum in log normal. So this one is the numerator, this one is the sum of all.
And there is no way, for example, to the sum of the log normal.
It's not going to be. We could say this because we know from CLT, central limit theorem, we've got a large number. The sum of any IID random variable should lead to a normal. But then the moments we're going to compute are going to be the same approximation as summing the moment as we do them. So doing the transformation ends up being the same thing.
Because I feel this is where it's coming from, the discrepancy.
I don't think it's in the sum, because from central limit theorem, we would get the same moments we're currently obtaining.
I mean the discrepancy of going over one.
Exactly.
Because like as any number, any positive number, if you're summing one of the part of the group on the sum of the group, you should end up with something within one.
No. What do you mean something?
Wait.
We're gonna you see that the sum here is gonna be. You see the numbers are between minus 0.5 and 0.5, and the sum is something 1 with standard deviation of say 1 as well.
Yeah, but this is the probability of one class, as in.
This is the probability of each. This is all the zi. This is the sum of all the n real.
Yeah.
And this is for just one class.
Yeah.
For me, if I would have to suspect, you're right into thinking that if your denominator is wrong,
Yeah.
it's going to affect, but the more terms you're going to have in your denominator from CLT is going to be more and more exact. As I'm going to increase the number, this is going to get better and better. Okay, however, what I suspect is that a little off in the numerator, that might be why it's going to screw it up. Because we can try it, for instance, I'm going to increase it to 500. Okay, and we're going to keep it to 1. And I'm pretty sure that my log normal and normal are going to fall on top of each other. Because now my approximation is going to be really, really good. You see that it's getting better. Because I think my CLT for my normalization constant kicks in, and I'm getting better. So now it's much longer because I need to do all the Monte Carlo samples. But it's not yet on top, but it's better.
But if you take the log of each individual in the numerator, but when you take the sum of the denominator, you keep them the same, and then you take the log at the end. Is there?
Yeah, I think it's going to be log on top. I'm going to transform each of those into normal, sum them up, and transform them back as a log normal.
But if you transform the top with normal, can you transform the stuff within the sum to log normal as well? Or this is going to
repeat that?
Because you're transforming the numerator, each individual one, into log normal.
Yeah.
So when you take the sum, you're keeping them as normal.
Yeah.
And then at the very end, you make it normal. Oh, because the sum will log normal. But can't you make each individual inside the sum also log normal? Maybe you will make it normal.
I could, but I would need to double test it. But my intuition is that the output moments you would get would be equivalent to the sum of the moments of each individual. And by assuming them as normal, this is what you get anyway.
Yeah, it's going to be the same error, but you get to it in a different path.
Because when you want to compute the global sum from the log normal, you would obtain it by summing the mean and variance of each of those log normal, which is exactly what we do anyway. This is equivalent to assuming them as normal. The resulting moments are the same.
Or maybe you could assign weights related with the error. I don't know.
To which
Like,
error?
with the approximation error.
Yeah, but we don't know it.
Yeah.
Because now I can compute it, but in reality we won't be able to compute it. But seriously, the approximation error is fairly small. And so far I suspect this is gonna work out of the box. Because here, this is an extreme case, but in more normal cases, the error, given all the approximation we have, it's not too bad. And given everything we have to handle here. So I think this is gonna work pretty well. Again, it's all approximate inference, but you have to choose between approximate inference and exact deterministic completely wrong.
Yeah.
So even if we're approximately right, it's better than being surely wrong. So the alternative is to use this is too exact
The battery is good.
as well. So yeah, maybe the streaming is taking more energy than usual. But yeah, so basically what I was saying, what was I saying just before? The approximation is good and it should work well. At the end, we're doing approximate inference, so this is going to be another part of the approximate inference.
One last comment.
No, these are welcome.
We don't know the errors, but we know where they're gonna happen. Like in the scenarios that you showed, where like you have large variance close to the bound, like no.
Yeah, but it's not, I don't think it's a good trick to start to build a model for predicting where inconsistencies are going to be.
And just the idea is that like whenever we're transforming from normal to log normal, there are some scenarios that would be perfect, and there are some scenarios where we can be off. So I'm just saying that if we maybe focus a little bit on, we know where it happens, if we can assign like some weights to.
That's true. As a second phase, when we're going to have tested it and see, if we see that the limitations are really in that formulation, we might go back and say, okay, how can we improve it? And one way to look at it would be those edge cases and see what we can do to improve those edge cases.
This is like really nitpicking. It's already great. I mean,
Other questions, comments? Perfect. I'm going to save my last bit of battery I have before it dies.